Hello everyone, let's continue our discussion on identifying the noise margin high and low for the set of inverters on which we did some spice simulations. So we already did some set of spice simulations where we increase the size of your PMOS twice, thrice and so on with the size of NMOS. So we'll use those set of curves, okay, and we'll try to identify the point at which your slope is -1, and then we will evaluate the noise margin high and low. Okay, the purpose of this experiment is to find out when you vary your PMOS size with respect to NMOS by some integer of NMOS, how does your noise margin high and low varies? And depending upon the values of the noise margin high and low, that will decide the CMOS inverter robustness. So we have to basically prove at the end of this particular video that the CMOS inverter is robust, is immune to your noise variations. Okay, so let's try to identify what are those numbers. So you have this curve, the DC transfer characteristics for your PMOS is equal to NMOS, for your PMOS width is equal to NMOS width. Okay, so the first step is to find out the point on this particular curve where your slope is -1. So this is the point on which where your slope is -1, and we just need to extend them, and we need to find out the noise margin high and noise margin low value. So in this case, the noise margin high will be 2.5 minus something about 2.2. okay, and over here the noise margin low will be 0.3 minus 0.0. so this will be 0.3 volts, and these are the 0.3 volts. So your noise margin high is 0.3 volts. Okay, your noise margin low is 0.3 volts. So what does it say? It says to us that your PMOS with a width of WP and your NMOS with a width of WN, it's able to sustain noise which are lying in this range. Basically any voltage that lies in this range will be considered as logic 1. Any voltage value that lies in this range will be considered as logic 0. Okay, so the broader it is, the more helpful it is for us, because in that case it will be more immune to noise. When I say it is more immune to noise, anything, for example, if this point was lying somewhere over here, so you have a wide range of noise available over here. So all this set of noise which will be, all these variations of noise which will be available between this point and this point will be considered as logic 1. And that basically says us that the CMOS inverter is pretty much immune to noise. It can just gulp those noise variations that is available over here. Similarly, if you had a wider noise margin for your NMOS as well, any variations that you see in your supply voltages or in your ground voltages, which we'll be talking about in some time from now, there are issues like power supply variations. So any noise variations which you see at the 0 voltage, that will be just gulped by the NMOS, and because since you have the NMOS low, or the noise margin low, as a very high value. So right now it's only 300 millivolts, so bigger the better for us. Okay, so let's see how do we increase the noise margin. Before that, let us try to identify the noise margin variations with respect to variations in the PMOS and the NMOS width, or basically the PMOS width. Okay, so now when you increase your PMOS width by twice of NMOS, you see the noise, you see this is the curve, and this is the point at which your slope is -1. Similarly, this is the point at which your slope is -1, and your noise margin high is increased by 0.5 or 0.05 volts. Basically this is 2.5, and this somewhere around 2.15, so that comes to about 0.35 volts, and your noise margin low remains the same. So the reason, if you see, once you increase your PMOS size by twice of NMOS, the PMOS is the one that is responsible for holding the capacitance, holding the charges on the capacitance. Okay, so basically PMOS is the one that keeps the capacitance charged, and when you increase the PMOS size, the resistance path, it creates a low resistance path from supply to the capacitance, and as a result of that, it's able to hold the charges for a longer amount of time. Okay, and as a result of that, if you see, the noise margin high is increased by 50 millivolts. So as and when you try to increase the PMOS width, your noise margin high will increase, but again there are some limitations, and we'll talk about limitations in some time from now. Okay, next we'll try to increase the PMOS width by even more and see what happens. So you increase the PMOS width by thrice of NMOS, and as a result of that, if you see, the noise margin high has increased even more, let's say 0.4 volts or 400 millivolts, and the noise margin low is still the same, is 0.3. And the reason, if you see the increase in the noise margin high as and when you increase the PMOS width, is because PMOS is the one which is responsible for holding the logic 1 on the output capacitor, whereas NMOS is the one who is responsible to NMOS is the transistor which is responsible to hold logic 0 on the output capacitance. So that's the reason, if you see, you increase your PMOS width, you see an increase in the noise margin high value. Okay, so we'll look into another case where we increase the PMOS size even more. So you increase the PMOS size by 4 times of NMOS, you see a 20 millivolts increase in your noise margin high. So that's very minimal. Okay, so as I said, there are certain limitations. If we can't keep on increasing the PMOS width, assuming their noise margin high will go on increasing. There is certain equations that models this one. Okay, and so at this point of time, if you see, the noise margin high is 0.42 volts, and in this case your PMOS has become even more stronger than your NMOS. As a result of that, if you see, there is a drop in the noise margin low, because your NMOS is now become weaker than your PMOS. Okay, and as a result of that, you see there is a drop in the noise margin low, because the ability for the noise margin for the NMOS to hold the logic 0 has diminished because of the strong PMOS which is present on top of it. Okay, so this is your NMOS whose noise margin low has been reduced, and your PMOS, the noise margin high, has been increased by 20 millivolts. Okay, moving on to the last one. If you see over here, the noise margin high, when you make your PMOS size 5 times to that of NMOS, your noise margin high is almost comes to a static point. Okay, so this is the range at which you can see your PMOS and NMOS varying. Your PMOS and MOS width varies your noise margin high and noise margin low. So noise margin low has not been affected much, it's only 30 millivolts, but noise margin high, we started from 0.3 volts and it is now 0.42 volts. So the range is 120 millivolts, which is still acceptable and which still proves the CMOS inverter robustness. So you vary your, so let's try to plot, or let's try to bring everything in a table. So you we have this table. It says that this is with the variations in the PMOS sizes. If your this is the column of PMOS, this is the column of the way the PMOS width varies. This is the noise margin high, noise margin low, and your and the switching threshold. So switching threshold we already talked about. So in case, let's say we design a CMOS inverter whose switching threshold is supposed to be 1.2 volts, and the noise margin high and noise margin low is being designed to provide a switching to provide a value of 0.35 and 0.3 volts. Okay, but while fabrications, due to some fabrication imperfections, which I'll be talking about in the following lectures, due to some fabrication imperfections, you don't get exactly WP equal to twice of WN, but your WP increases slightly, let's say 2.2 times of WN, or it decreases to 1.8 in that range. So we need not worry about that, because the variations of your noise margin high and noise margin low is in the range of 100 millivolts, which is quite fair enough, and it's like acceptable for us. So that's the point of showing the CMOS inverter robustness in terms of noise margin high and noise margin low. Let's take another example. For example, we designed a PMOS or NMOS in such a fashion to give us a switching threshold of 1.35 volts. Okay, and to give a noise margin high and noise margin low of 0.42 and 0.27 volts. Okay, but because of the fabrication imperfections, if you see, the WP might be 4.5 volts or 4.5 times of WN maybe, and let's say this is 3.4 or this is 3.5 times of WN in this range. So in that case we need not worry, because your CMOS is pretty much immune to those variations. It is basically only 20 millivolts change in the noise margin high and 30 millivolts change in the noise margin low, and on top of that there will be about 150 millivolts of switching threshold. So we need not worry about the operation or the behavior of your CMOS. You will get what you want, but with a plus minus of 5% variation, or not even 5%, it will be about 2 to 3% variation. Okay, so that's what about we were talking about the CMOS inverter robustness. With that said, we can conclude one thing: this area of your CMOS inverter, or this area of our CMOS inverter, can be used for digital design, because digital design is a set of design where we care about logic 1s and logic 0s. So anything which lies in this range can be termed as logic 1. Anything that lies in this range can be termed as logic 0. And this particular CMOS inverter is very much prepared or ready to be used for a digital design. On the other hand, if you're looking for an amplification factor, if you're looking for an inverter that can amplify your input voltage to some output voltage, this is the best area to be used for, and that's basically an area which is used for your analog design. Okay, so that's all we had, that's all we had in this particular section for noise margin. In the next section we'll be moving into the power supply scaling. So we talked about our scaling. When you move from 250 nanometers to, let's say, 20 nanometers, there is a power supply scaling as well. What does that impact on CMOS inverter, and how your CMOS inverter is robust even to power supply scaling? So let's try to look into all this in the next video. Thank you.